Hello everyone and welcome to my channel. So on this video we will see the advanced construction technology, which is known as an overview on precast construction technology, which is also known as a Lego construction. This technology is very advanced in the field of construction technology. So that is also known as the prefabricated construction technology as well as the precast construction technology. So let us start with the this technology. So this will be our flow of the video. So first we will see the overall about the precast technology. What is precast technology, its benefit and its difference with the cast in situ construction process. Then second we will go through the manufacturing process, how the elements are casted in factory. Then we will see the design consideration as well as the connection of the precast elements. Further, we'll go through the tolerance. What are the tolerance as per the codes, Indian standard codes as well as the foreign codes. Then we will pass on through the logistics and erection of the elements. And lastly, we will see the product test and its performance. So first let us discuss with the difference. So on the left hand side picture you can see the precast construction, and on the right hand side it is the cast in situ construction. So the major difference between precast and cast in situ construction is like, if we talk about the precast, the each and every elements are casted on site or on factory depending upon the situation. So precast means elements are casted on the ground, on one of the shaded area or the factory, and then it is transported and erected to the site. Either it can be a single module construction. So here this photo is the module construction in which the full box is casted at a time, or else there will be individual elements like beam, column beam, slab, landing, staircase, etc. On the other side, if we talk about cast in situ construction, the cast in situ construction is like brick by brick construction, which is like a normal traditional construction where formworks are used to build the structure. So here you will see the best way of the difference between the traditional construction and precast construction. So first we'll see the traditional construction, which is step-by-step construction. So in which we have to in which there is a use of formwork and that is leveled, and then the concrete work is done where higher accuracy is required, where there is a chance of lack of quality as well as curing as compared to precast construction. On the other side, if we see the precast construction, so each structural elements are pre-planned, executed, transported and erected in position with high accuracy of supervision and precision in controlled environment. Also on the left bottom side you can see this is the precast column, this is the precast beam, and on the top the another precast column is connected with this connection part. So we will look each and every connection detail as well as each and every elements, how they are casted and erected on the site. So these are some of the advantages of precast technology. So first, it is design optimization. Second, it is safe and sustainable site. Third, optimum resource management. Fourth, it is the energy efficiency solution. And fifth, it will improve the environmental quality. So if we talk about the process, so process starts with the concept and planning. So the main core part of the precast is the concept and planning part. So here in this part the elements will be break down into number of pieces, and it will be pre-planned on at a micro level, and then it will be passed on to the design, where design will be done, and after that the production will be carried out. After the production, the elements will be transported using the special vehicle which is known as the logistics part, and then the special trailers will be moved to the site where the elements will be offloaded from the trailer, and then it will be erected on site. After the erection, the finishing work will be done, and then it will be handed over to the client. So this is the uh, single line process for the precast technology. So we will go through each and every activity on our further slides. So these are the element types we will look into this video. So first, on the first picture, you can see hollow core slabs. These are the slabs used as a covering material. So this will be used as a slab. So second, we will see the frame structure, which is known as precast beam and column. Then third, we will go through the landing and staircase, as well as there are many special elements, such as here you can see this is the dome structure, which is in precast, segmented precast. Each and every element are individual, and then it is erected on the side. So there are many special elements like a dome structure, then chhajja, then there are many barriers, road barriers, then underground structures, etc. So in this video we will see the building elements. So first, let us start with the hollow core slab. So here you can see in the picture, this is the hollow core slab, which has the core on the center. So this is known as the core. That's why the product name is known as hollow core slab. Why it is said as a hollow core slab? Because it has cores in between the slab, which will make the material, which will reduce the weight of the slab, as well as it creates the air between the slab, which will ultimately reduce the temperature of the room. So hollow core slabs, here in this picture, blue color, you can see this is a single one piece of hollow core slab that will be laid one by one, and this floor will be covered using this product. So basically, hollow core slabs are the dry mix product. So what is dry mix product? As everyone know, in cast in situ we use slump concrete, which is around 150 to 160 mm slump is used. So that is known as the wet concrete. If we talk about dry concrete, the dry concrete is like it will have a zero slump concrete. There will be no slump. When the material is prepared, it is prepared as a control mix, where there will be a water, but at a moisture point only. So when we take the material and when we feel in hands, then at that time the ball will be created using that concrete. So that is known as the dry mix concrete. The dry mix concrete is used because to produce this kind of structure, to produce this kind of product, we use a machine. So we will go through what is the machine, what type of machine is used. We will see in the further slides. So if we talk about the width, this is the width of this slab. So this will be 1.2 meter fixed, because this will depend on the machine size. So machine can produce a width of this slab as 1.2 meter. So the normal width of the hollow core slab is 1200 mm. So this is the machine that is used to produce the hollow core slabs. So here you can see this is the extruder machine, and from the bottom it will create the hollow core slab. And here you can see there are some of the tubes on the center that will create the shape, and it will give the shape to the slab. And here you can see the core tube that is extruding the material, and the shape is retained. And on the right hand side bottom, you can see the screw that is used to push the concrete. So we'll see how this machine works, and we will also go through one of the video in which you will clear how this machine will work. So there are some of the parameters on which this machine works. So that are the Archimedean screw. There is a compaction and anti-compaction factor that is very important for the production of hollow core slab. There is a core tube. There is a side former. Here you can see there is a side former that gives the side shape of the slab. As well as we have the smoother plate. So here you can see the smoother plate, which will give a smooth top surface of the slab. And at the bottom we have the steel plate, which is known as this a steel bed, on which the slab is casted and machine will run on that bed. So we'll look into the video how it works. So let us discuss some of the technical detail in which the hollow core slab is designed. So these are some of the design consideration for the hollow core slab. So the starting with the material selection, it is very these 7 points are very important while designing the hollow core slab. So first let us start with the material selection. So the grade of the concrete and concrete type is very important to achieve the strength and to gain the product specifications. Second, there is a pre-stressing wire. If the hollow core slab are pre-stressed, in which the strand wires are used, so there will be a use of pre-stressing steel that will be pre-stressed, and then the concreting will be done. The second thing which comes into the consideration is the dimension specification, where the thickness of the slab is important, because thickness of the slab depends on the loading type. And the second point we have is the width of the slab. So as we have seen that the width of the slab is standard, that is 1.2 meter in width. Third point is the span and loading. So the span length is also an important factor, because the hollow core slabs are one-way spanning slab, in which if the loadings are more and the span is more, then we have to increase the thickness of the slab as well as the strand pattern, which will be designed as per the given loading. And yeah, as we have seen that loading type is very important for the selection. Fourth parameter is the pre-stressing design. So in the design, it is selected that how many number of strands will be used and what will be the strand pattern or strand layout, and then it is decided that how much force has to be applied for a given load. Fifth, the hollow core configuration, in which the core dimension and its thermal and acoustic parameters will be verified. Sixth, there will be a structural analysis in which the bending and shear capacity of the hollow core slab has to be checked, and it should be controlled for the crackings. So there should not be any cracking. So the structural analysis is very important while designing the hollow core slab, where we have to check for bending and shear. And the last point we have is the connection and connection and supporting. After the production, the main part comes is the connection of the precast elements. So for the connection, the first point is the bearing. Bearing means the sides on which the hollow core slab will be rest. So that is known as the bearing, which will be on both sides. And second point we have is the connection type. So we will see how these precast slabs are connected with the beam and how the load is transferred to the beam and beam to the column. So this was the design consideration that are to be considered while designing. And yes, pre-stress loss is one of the important thing that has to be considered while considering considering the force that has to be stressed. So there are many losses that are considered while designing. So there are elastic shortening, there is shrinkage loss, there is creep loss, there is friction loss, there is anchorage set, there is steel relaxation. So this all parameters will affect the pre-stressing force, which is ultimately known as the loss in the pre-stress. So this is also considered while designing the slabs. So here you can see in the figure B, as we have seen that the width of the hollow core slab is the standard, that is 1.2 meter. So this is the cross section of the slab, and above that you can see in the dark color, that is the additional concrete that is done on site to connect all the hollow core slab. We will discuss this part in our further slides. So if we see the standard table weight of the hollow core slab, there are many thickness of the hollow core slabs are available depending upon the span and the loading condition. So the first thickness we have is the 150 mm, second is 200 mm, then 265 mm, and up to 500 mm, depending upon the machine type. There are two major machines that are used. First is known as Nod Impianti, and second is the Alimatic. So depending upon the machine type, the thickness of the hollow core slab varies. There is also 120 mm thick hollow core slab is available. Even we have 100 mm hollow core slab. Even we have 75 mm hollow core slab. But in that case, the machine type varies. So this is the standard product starting from 150 mm or 120 mm to 500 mm thick hollow core slab. So this column, you can see the number of cores. This identifies the core number. So in this 150 mm slab there will be 8 numbers of core. In 200 mm slab it will have 6 numbers of core. In 265 mm slab it will have 500 mm core, and simultaneously for 500 mm thick we have 4 cores. You can see 1, 2, 3 and 4. So here it shows the self weight of this slab in kilonewton per meter square, and here it shows the joint weight. What is joint weight? So this part is known as the joint. So the joint between two hollow core slabs are concreted, is poured by a special grout, and that joint weight is considered to be as 2.36 kilonewton per meter square for 150 mm thick hollow core slab. So let us start with the manufacturing process. So first, the hollow, if we have already seen and understood what is hollow core slab, how it is produced. Now let us see what are the manufacturing process that is involved. So as I told you earlier that the hollow core slab are casted on the steel bed. So here you can see this is the steel bed, and it is having a fixed width of 1.2 meter. It has a guide rail on both of the ends to run the machine on the this rail, and we have the hot water pipes below the bed, which will use as a curing system, which will enhance the strength of the concrete, which will give the early strength of the concrete. So this system is known as steam curing system. So first step is the cleaning of the bed and laying of the strand wire. So here you can see this is the bed master that is used to clean and wipe up the bed, and then the steel wires are placed along, and then the special lock that is known as this wedges and barrel that is used on both ends. Using these locks, the both side of the strand wires are locked, and then the stressing will be done. So here you can see this is the cleaning and laying of the strand is done, and then this is the wire gauge that is used to hold the strands on the position, and this is the standard chart for the strand wire and its physical property, that is as per IS 14268 2022. There are three types of wires, strand wires, that is plain wire, indented wire and compacted wire. So here the picture, in the picture you can see this is the strand wire that is used, and here you can see in the figure this is the steel rope. Actually let us understand the concept how this strand is prepared. What is strand, what is wire, and what is tendon. So when a single wire, this part, the single wire is known as wire. When number of wires, this is wire, and when numbers of wires are twisted in a single wire, that is known as the strand, and when number of strands are twisted in a group, that is known as the tendon. So here we are using strand wire. So here you can see there is a here indicate the P indicates that is a plain wire. Here C, it indicates that it is the compacted wire, and we also have the indented wire. So depending upon the design, the strand wire has to be used, and these are the tension capacity of the wire, cross section area and other parameters that are considered. So after laying and locking the wire on both of the ends, now this stressing will be done. So the end from where the stressing is done, that is known as the live end, and the another end where we have locked the wire using wedges and barrel, that is known as the dead end. So here you can see this is the stressing machine that is used to pull this wire using this stressing gun, and we have the safety net or safety shield that is used for the safety purpose while stressing this wire. So here you can see this is the red color, that is our strand wire. So first, when we start with these the process of stressing the wires, let us say for example we have to stress a wire at 100 kilonewton by 100 kilonewton of the force. So first thing what we will do, we will just give the initial elongation, initial force will be given, that will be like 10% of the total force. So in our case we have considered 100 kilonewton as a total force, so we will first set a 10 kilonewton, that is 10% of the total force, to avoid this self sagging of the wire. So this is this sag due to the self weight of the strand wire. So to avoid this sagging, we will first apply a 10% of the force, and then after that we will mark on the wire, and then we will give the remaining 90% of the force into the wire, and we will measure the elongation. So the elongation formula is like PL upon A, where P is the force, L is the length of the wire from jaw to jaw, or we can say lock to lock length, and A is the area. This area is the jack area, and E is the modulus of elasticity for the strand wire. So this graph you can check this graph in IS 1343 2012, which determines the calculation of the elongation. Next step is the preparation of the concrete mix and its transportation. So in this kind of facility, there generally people use the advanced technology, that is fully automated precast concrete plants, in which the concrete will be transported into the flying bucket system, which will be run overhead, and there will be automated system in which the concrete will be flow in a system, and it will be distributed into the distribution bucket, and through the distribution bucket it will be poured into the extruder machine. So here you can see this is the extruder machine that is producing the hollow core slab. So in this video you can see this is our machine, extruder machine. In the front we have the protection, and here you can see the concrete is flowing out of the machine. Now it will start making the hollow core slab. It will create and form a homogeneous shape of the hollow core slab. So here on the top the smoother plate is working, and on the sides you can see these are the side formers that is used to create the side shape, as well as this is the top smoother plate. So here you can see up to here it will be the waste, because it will not suddenly create the shape of the slab. So from here you can see how compacted and very nice slab has been created. Now here you can see this is the wire brush that is fixed on the top of the machine, so that the top surface of this slab will be roughened to have a bond between the dry concrete and wet concrete. So here you can see this is the top surface of the hollow core slab, very smooth, and finishing level is very great. So here you can see this is the wire brush that is used to rough the top surface of the slab. So here this is the side former that is creating the side shape of the hollow core slab. Yeah, so here you can see very clearly this is the shape that is created by the side former, and this is the groove or key that is used to lift the hollow core slab after it achieves the strength, and it will be cutted and then it will be lifted. So as soon as the production, after the production of the slab, the slabs are covered using the tarpaulin sheet. Tarpaulin sheet are the heavy GSM sheet which avoids the loss of water from the concrete, and it also creates a self-curing type of environment that reduces the manual water curing. So it will help us to gain the high strength at very lower time. So here this is the cutting machine. After gaining the strand wires will be released, and then the slab will be cutted as per the required length. So this is having the diamond blade cutting blade will be there, which will be rotated, and the slabs will be cut into the required length. Uh, the most important part is the sampling of the concrete. So at the production, the sample are collected, and cubes are filled in the standard manner to check the strength at the early stage. As it is a precast technology, the requirement of the strength is very high. So we required minimum 50%, we required minimum 70% of the strength to distress the wire, and that has to be achieved in 18 to 20 hours. So it is very challenging to get 70% of this strength. Let us say we are using M50 grade of concrete, so we need minimum 35 MPa, which is 70% of the 50 MPa that is required in 18 to 20 hours to distress that particular hollow core slab, and then cutting and then lifting will be done. So the strength is the very important parameter. As I told, this concrete are zero slump concrete, so it is a beneficiary to get the high strength at the minimum time. So the minimum grade of concrete that is used in the hollow core slab production is like C15 and C60. That is the grade that are used. So the minimum grade for the production of hollow core slab is 50 MPa. So this is the design and connection details for the hollow core slab. So now so these are the design codes that are considered while designing the hollow core slab. We have the design and construction of the core slab units. We have structural use of concrete. We have the common rules for the concrete production. We have precast pre-stressed hollow core floor system, and also we have hollow core slab, and we have the PCI manual. We have PCI books as well as ACI codes for the consideration of the hollow core slab. So here you can see the strain and force distribution in the hollow core slab. This is how the strain and force are distributed using the strand wire and concrete. This is the concept of the concrete and strand, which will be used in distribution of the force and all the stresses. Some of the other important IS code and BS standards that are used for the design and connection points, that is IS 111447, IS 15916, BS 8110. So this is, as we have already seen, these are the different thickness of the hollow core slab. This is the core, number of cores, and here you can see at the bottom the dotted part is the strand wire at the bottom, and we have the top strand as well. On the right hand side you can see the graph in which it shows the thickness type as well as the loading requirement. So this is the thumb rule for the selection of the thickness of the slab. So let us assume we have the span of 6 meter. So 6 meter of span with 150 mm hollow core slab, it can carry a load of 2 kilonewton per meter square. So if there is a room with a 6 meter of span, then we can go with 150 mm hollow core slab that can carry 2 kilonewton per meter square load. So this is the thumb rule for the selection of the hollow core slab thickness, but it is always mandatory to have a design check. It is the design is very important. We cannot rely on this type of graph. This is just for an indication that it can be used, but ultimately the design is very important for this kind of structures. So here you can see this is the connection detail of the hollow core slab. So either hollow core slab can be rest on the wall with the corbels on the wall or a nib on the wall. So the slab will be rested on the nib and the load will be transferred on the nib and from the nib to the wall panel. Second connection we can go with is the steel corbels. So here this is the concrete corbel that is used to support the slab. Here this is the steel corbel that is used to transfer the load. And third we have rebate. Rebate means there is a recess in the wall, there is no projection items from the wall. Here you can see there is a projection item, that is a concrete corbel, and here there is no projection in the wall, but we have the recess in the wall. In that the hollow core slab will be rest. So this is the better option in which it will provide a good aesthetic view. This kind of corbel connection can be used in the parking area or in some of the special structures. So here you can see this is the hollow core slab, and above that we have the connection details which will be covered up with the concrete topping, and the casting will be done. So this connection detail, and we will see in the further slides. Yeah, so this is the better view and visualization of the hollow core slab. So this is the hollow core slab. See, this is 150 mm thick hollow core slab that is rested on the steel I-beam. It can be either rested on the steel beam, or it can be rested on the on an RC beam. It can be rested on the corbel. It can be rested directly on the wall using the rebate connection. So it depends. So if it is a steel structure, then we can directly support the hollow core slabs on the steel beams. So here on this table you can see this is the table where it shows the bearing requirement. As I told, to rest this hollow core slab we need the minimum bearing. So what is bearing? So bearing is the minimum area that is required, or minimum width that is required to rest the hollow core slab. So in case of concrete or a steel material with a slab thickness of less than 265 mm, we required nominal 80 mm of the bearing. That is minimum requirement to rest the hollow core slab. If the thickness of the slab is more than 320, it is recommended that it requires 100 mm bearing. This also depends upon the design, because design has to be checked for a given loading type and the transfer mechanism. So this is the minimum requirement that has to be considered. Yeah, this we have already discussed. So here you can see this is the brickwork, and from here both sides the hollow core slab are rested. So that is this kind of connection is known as wall, and above that there is a hollow core slab that is resting from both of the ends with the required bearing. Second type of connection, that is on the precast, or we can say cast in situ beam. So this part is the beam that is having the recess on both of the side, and from the both ends the hollow core will be rest on the required bearing. So third condition, we have the load bearing wall, the same condition, so in which there will be a load wall below, then there will be a slab, and there will be a wall above the slab. So this kind of load bearing wall can be used for the connection. And the last we have the steel beam, in which we have already seen. So this is the steel beam, and above that the hollow core slab are laid. Hollow core slab can also be used as cantilever structures, but it is preferred that it should not be more than 1 to 2 meter, because these are not very healthy for using it as a cantilever structure, because for the cantilever structure we need to have the top reinforcement. So here you can see we have to use the strand wire on the top surface of the concrete. So this is the cross section, longitudinal cross section of the hollow core slab, in which we have to place the additional top bar to have the cantilever projection of the hollow core slab. So yes, the hollow core slabs can be used as a cantilever projection also, but it is having some of the limitations where we cannot go more than 2 meters. It also depends upon the loading type. This kind of cantilever structures can be used for the balcony projections, for the bay windows, for the extension part, or for the decorative purpose as well. So if we talk about the supporting structure, so this is one of the advanced supporting system that is used, that is known as the delta beams. As we have already seen the supporting structures, so we have seen this 4 type of supporting structures, where we have brick wall, we have precast beam, we have a steel beam, we have load bearing walls. Now we have an advanced kind of connection, or we can say the hollow core placement technology, that is known as delta beam. So here you can see this is a delta beam. Delta beams are steel beams that are produced in the factory depending upon the requirement. So why steel beam? Why not we cannot go with the concrete beam? So the advantages of delta beam is that can be used for a longer span, that is flexible for opening, that has additional room height, it is fireproof, it has low heat, and it reduces the cooling cost, it has fireproofing integrities, it is easy and space saving. So let us first understand how delta beam and precast beam are different, and how delta beam are more efficient than the normal beam. So here in this figure you can see this is the cast in situ precast, or we can say cast in situ beam or precast beam. So where the depth of the beam is 1.5 meter or 1500 mm, and where if we use the delta beam, then the overall depth of the beam that can be 775 mm or 0.775 meters. It can be considered to be 775 mm, which reduces almost 50% of the depth can be reduced by using this kind of supporting system. The another advantage is that we can use this kind of steel beam for longer span. So the first point was it will reduce the depth of the concrete, it will reduce the depth of the beam, which will give you the good clearance of the room. Secondly, it can be used for the longer span, that is also it will provide a good aesthetic view. Let me show you the clear picture, we will understand. So here you can see in the figure A, there is a steel column, and above that there is a steel beam. So this steel beam is the delta beam, and on the figure B you can see above the delta beam, that is steel beam, the hollow core slab, precast hollow core slab are rested on the beam. On the C you can see the side view of the beam to slab resting part, and then lastly on the figure D, this structure, which means steel beam as well as the concrete slab, will be concreted and all the joints will be filled, so it will act as a one single unit. So all the loads will be transferred from the precast hollow core slab to this steel beam. So here you can see in the figure B that there is no height variation that is seen between the delta beam and precast hollow core slab. if we are using this kind of RCC structure or RC beam, then the depth of the beam will be more, and that will be visualized here. So this is one of the benefit. Now let us see the openings that has to be provided in the hollow core slabs. Yeah, it is very important to provide the openings for utility passage, or to run the MEP, to run the mechanical pipes, plumbings, etc. So to create a space, a special beam is used, that is known as the spandrel beam, or we can say saddle support. So here you can see these are the saddles. Saddles are a kind of a steel beams that is used to transfer the load on the sides. So let us assume this is one of the floor in which this is the requirement of the opening. So yes, this hollow core slab will need some support to rest here. So to rest this hollow core slab, we will use this kind of beam that is known as the saddle beam, or that is also known as the spandrel beam, in which this load of this slab will be transferred 50% on the right hand side and 50% on the left hand side. So this kind of openings can be provided in the hollow core slabs, or while erection we can make this kind of openings easily, but this beams has to be designed by specialist. So yeah, this we have already seen. This is the precast or cast in situ beam, and on the both side we have the hollow core slab, and above that we will do the concreting on site to make the structure as a homogeneous unit or a single unit. So this topping that will minimum 65 mm topping is required to cover the hollow core slab. In between there will be a reinforcement cage that will be tied, and it will be connected with the beam reinforcement. So here you can see on the bottom side the single unit after making the topping on the hollow core slab. Let's say hollow core slab are placed, and above we have placed the cage, reinforcement cage, and then the screed or topping is done. So after the application of the load, this is the way that the slab will be distributing the force, and this kind of action will be created. Let us see how the special kind of suspensions can be used to line up the MEP requirements. So yeah, so lightweight suspensions as well as heavy suspensions can be connected below the hollow core slab. So for that, for lightweight suspensions such as electric conduit and ceilings, or light duty devices such as light, fan, or some of the pipe works that can be hanged in this kind of system using the special bolt that has to be drilled and that will be fixed in the core, that will take the load of this kind of suspensions. So for the heavy, in case of heavyweight suspension system, such as heavy equipment loads or other loads like motor, or we have a huge pipe, so in that case we have to use the steel rod, because we cannot hold that part from the bottom of the slab, because due to heavy weight it will not sustain, or it is not having the capacity to take the load of that particular part. So in that case we will use a special bolt that is connected from the top of the hollow core slab, and it is suspended down to the bottom of the slab, where this kind of special suspensions will be connected by the steel rod, and this steel rod will be connected above the hollow core slab, which will be concrete, and with concrete will give a good bonding of this rod. So there will be a good load transfer mechanism for this kind of suspensions. So yeah, we can also we can also make the cutouts for the MEP, or we can say cutouts for the light points wiring where we required. So here you can see this is the hollow core slab, and as I discussed, these are the reinforcement cage that is placed before concrete, as well as the MEP pipes are run. These are the conduits that are run throughout the slab to for wiring purpose, and all the at the required points. So here you can see at the bottom, this is the top side, we have placed the pipe. At the bottom we have hole. This kind of holes are made in the factory where the concrete is in wet condition, or we can say where the concrete is not matured. So at that time this kind of drilling will be done on the plant, and then at the side the MEP pipes, or we can say conduit pipes, will be run throughout to make all the connections possible. So after all these connections and placing the reinforcement and pipe, and tying up with the reinforcement, about now this part will be poured with the concrete. So this concrete will flow between these hollow core joints also, so that will create a one unit that will be helpful to transfer the load easily. So here you can see the hollow core slab, and it is provided with the minimum cover requirement, and we have this both way reinforcement on the top of the hollow core slab, and this part will be covered up with the concrete, that is known as the topping. So here you can see this is the joint consideration. So for the joint, a special kind of reinforcement bar, or we can say a bent bar, is used between the joints of the hollow core slab. So here you can see there is a V groove that is created, or that there is a V groove in which the concrete has to be poured, or in special case also the grout is used to fill this part. And yes, in this part the steel reinforcement is placed to, and that will be connected with this top bar of the topping. So this you can see some of the sections, in which here you can see the bearing part, and this is the longitudinal section. So if in case of the shear capacity, where in some of the structures there is a special requirement in which the shear capacity of the hollow core slab has to be enhanced, or we can say where the shear capacity is required to be on the higher side. So the shear capacity of the hollow core slab can be increased by filling up the hollow core slab. So how it can be done? So the shear capacity is increased by filling up the cores of the slab. Let us say this is the core. So in this core we have open around 600 mm of the core is open, and then the concrete will be filled up to 600 mm at the site on the time of the concreting of the topping. So this is how we can increase the shear capacity of the slab. That is very useful in special kind of structures, and we have a special conditions. So this table shows that the minimum thickness of the hollow core slab and the requirement of the which ultimately shows the shear capacity. So let's say we need to increase the shear capacity by 12 kilonewton. So it is required one number of core that has to be filled for achieving this particular shear capacity. So it depends upon the design criteria. So that is always recommended to check with the design in which this core has to be filled to enhance the shear capacity of the slab. In some case, to enhance the shear capacity, sometimes the steel bar is also placed in the core, and then the core are filled with the concrete up to 600 mm or maybe more than 600 mm. That is depending upon the loading and span of the slab, which will ultimately increase the capacity, shear capacity of the slab. In case of the narrow slab, or let us say part slab, so part slab are made by cutting the slab longitudinally. So let us say we have a room of 4 meter and we have to cover the room using the hollow core slab. So from the starting we will use 1.2 meter width of hollow core slab. So 1.2 plus 1.2 plus 1.2. So at the end we will require some part of the slab where we cannot use 1.2 meter of the hollow core slab. So for that we need to cut the hollow core slab for at the required part. So let us say this is the figure in which we have made the hollow core as a part slab. So this part slab are then filled with the concrete in this core. Here you can see this core are filled with the concrete to avoid the damage while lifting and placing of the hollow core slab. So this is how the hollow core slab are cut and the core are filled to avoid the damages while transportation and erection of the slab. Here you can see this is the end cap. The black portion, you can see this is the end cap that is used in hollow core slabs. This is because when the concrete is poured, of the topping concrete is poured, the concrete may flow inside the core and it can block the core. So to avoid that, the special kind of cap that is known as end cap that is used to cover these cores, so that these cores are this core has to be concrete free, because it will provide a good sound insulation, it will create a lightweight structure, it will give you the fire resistance, as well as it will be a thermal resistance roofing system. So now let us see the slippage allowance. Yeah, there will be some kind of slippage. We have already seen in the previous slide that there will be some kind of losses in the pre-stress due to thermal, due to shrinkage, due to creep. There are some percentage of loss that has to be considered as an additional part when we are calculating the required force for stressing wire. So this is the formula in which the slippage allowance is can be calculated. So let us say we will have one of the example in which we will consider that there will be a 14% of the pre-stressing loss. We are using 12.7 mm diameter, 12.9 mm diameter of the strand, which is having a tensile capacity of 1860 Newton per mm square. So this is the formula as per IS 1343 2012, that is pre-stressed concrete code, and by using this formula you can just put all the required data. So here it says that pre-stress loss that is allowed is 2.61 mm per strand. So I am assuming I have assumed as 14% of loss, and that can penetrate, or we can say there be a loss in elongation of 2.61 mm. So this is the loss that you can physically check in this slab using vernier caliper. By using the depth part, you can check the depth, which should not be more than 2.16 mm. So that is safe, or we can say allowed slippage in strand wire. So this is the effect of end slippage. When there is a slippage in the hollow core slab, then it will ultimately affect the capacity of the slab. So that's why we consider some amount of loss in the calculation of the force that is required in the strand wire to carry the load above the slab. So it is always considered to have the loss in the design. So this here you can see this is the tolerance that are allowed in the product. So if we check manual 135, that says about tolerance manual for precast and pre-stress concrete construction, where the length of the slab can be allowed plus or minus 13 mm. So length is the overall length of the slab that is allowed up to 13 plus or minus 13 mm. Then the width of the hollow core slab, width means we will say 1200 mm, that can be allowed as plus or minus 6 mm. Then we have all other parameters such as web width, depth, overall depth, top flange, bottom flange. So this all kind of tolerances that has to be considered, and this is applied for the production of the hollow core slab. So it is very important to consider the production tolerances. Here you can see N1 and N2, that are the opening size that is considered, or we can say a block out or cutout that is considered in the slab, that in which it has to be under the tolerance. So here it is given N1 block location of block and size of block, so that they have considered as 20 plus or minus 25% and plus or minus 13%. So this was all about the precast hollow core slab. So yeah, in this video we have seen hollow core slab. In my next video we will see the production as well as the erection of the precast beam and pre-stress beam. So we will see you in our next video, which will be on reinforced concrete product that is known as precast beam and pre-stressed beam. Thank you so much. Thanks for watching.